Alrighty, welcome back to operating systems. So where we left off last time, which was yesterday, we implemented a lock and it was crap. Didn't work. So today we get to fix it. So as an aside, in some courses you can actually implement locks with minimal hardware. So your hardware requirements can be as low as loads and stores are atomic, and your CPU executes instructions in order. And some courses they'll walk you through Peterson's algorithm or Lampard's bakery algorithm, which basically just tries to simulate, taking a number and then they call numbers in order, and that's the order you get served, which is kind of like a lock. Problem is that these are all computer science-y and they don't scale very well in the real world. No one actually uses this as a proper lock implementation, so I will show you the proper way we actually implement locks in today's day and age. So let's assume we have this magical atomic function. It is called compare and swap, and again, atomic means it either happens all at once or it doesn't happen. There's no in between. So this magical atomic function takes an address to a pointer and then two values, an old value and a new value. And what it will do is it will try and read the current value. If it matches whatever this old parameter is, it will change that value to be new, and it will do that atomically. And this compare and swap, will always return the original value at that address. So you're guaranteed, if I use it like this, if I do a compare and swap and use the pointer to that integer and then give it the old value as 0 and the new value as 1, well, this function will only return 0 if it successfully changed the 0 to a 1. Otherwise, if the current value is 1, it will just return 1. So this way, we can implement a lock. So if the initial value is 0, if one thread calls lock, well, it would do a compare and swap on that. Its current value is 0, so it would change the 0 to a 1 atomically and then return 0. Since it returns 0, well, while 0, that is other word for false, so it would fall out of this while loop and continue, so that one thread would make it through that lock call. Now, if another thread tries to call lock, well, the current value of that L is currently 1, so compare and swap will return 1, so 1 is otherwise true, so this while loop will just keep on going over and over again, and this way we only allow one thread to make it past lock at any one given time, assuming that this compare and swap function is atomic. So everyone agree with that? So this is an implementation of a lock. It works. Only one thread can make it past that lock function at any given time.
That should work.
Yeah, this works. So this is now safe, right? So it works as a lock. Only one thread makes it through at a time. But it still has that problem, well, if we only have one core on our machine and another thread has the lock, so the current value is 1, well, the other thread is just going to execute this while loop over and over and over and over again, and it's not going to make any progress, so we're just wasting some time. So this is a proper implementation of a lock. It just has that problem where it has that busy wait. So that lock is a valid implementation, and it's given a special name because it's actually kind of useful. It is called a spin lock. Why is it called a spin lock? Well, they call it that because of that while loop that constantly keeps on retrying it over and over again. And this compare and swap function that I used here, that is the atomic instruction that's supported on all your CPUs. On x86, they happen to call it comp exchange, or why? I don't know. They want to shorten it for some reason. What's it supposed to stand for? Well, it's supposed to stand for compare and exchange. Compare and exchange, compare and swap mean the same thing. So again, this is an implementation of a lock. It works, but still has that busy wait problem. So again, like if you have a uniprocessor system, so a system with only a single core on it, if you can't get the lock, you should be smart enough to realize that, well, you shouldn't retry or anything. Just yield, put yourself to the back of the queue, let the kernel schedule another process or another thread. Hopefully that one calls unlock, and then you can proceed. So if you however, have a machine with multiple cores on it, you might actually want to use a spin lock, because every time you read, well, some other thread, because it could have executed in parallel, might actually unlock that mutex. So it might be worthwhile to just try again, depending, because as we'll see, the implementation of a mutex is much more complicated than this. This is essentially one line for lock, one line for unlock. That's it. Can't really get much simpler than that. So any questions? Nope, we're good. We got a lock. It is a spin lock. All right. So here's what would happen if we tried to make it a bit more efficient. So we will change that while loop to do while compare and swap. So if compare and swap returns 1, that means some other thread has the lock. So we should just yield. So if we do this, well, now we have a new issue, and it is something called a thundering herd, because you might be in a situation where one thread has a lock, then 8 threads are trying to acquire that lock, and essentially all those 8 threads will just fight for each other as soon as you unlock that. So that's kind of a waste of time. So if you have 8 threads all fighting for the same lock, and it's a mutually exclusive lock, you know that only one thread is going to be able to get it anyway, so why would you let all 8 threads fight for it? Only one thread should try. Yep.
How would they fight though? I thought like after like the lock is released, like the first thread that comes will get the lock, and then the other threads will just yield as usual, and there will be no like complicated things. No?
Yeah, so the problem is exactly that. So if I have 8 threads, well, they all yield and they'll come back. So say another thread unlocks this. So we have 8 threads that are yielding. One thread unlocks the lock, and then all 8 threads are going to check. So the first one is going to acquire the lock and then pass, but all the other threads are just going to check again. 7 of them are going to fail, and you already know 7 of them are going to fail. You're wasting time waking them up and having them yield again, right?
So basically, like the procedure of threads coming back and going away again is a problem here.
Yeah, so say you have 10,000 threads.
Oh, yeah, I understand now. Thank you.
Yeah, so if I have 10,000 threads, I don't want, like, if I unlock it, I only know one of those 10,000 is going to get the lock. I don't want all 9,999 of them to just try again. They're going to fail. They're going to yield again. Why bother? So we want to fix that problem. So the other problem with the thundering herd is, well, they'll all try again, and you're not guaranteed which one of those threads is actually going to acquire that lock. So if 8 threads were waiting for that lock, well, all 8 of those threads should be able to acquire a lock before some new thread tries to acquire a lock. You want to be fair, maybe form an orderly line so you can reason about it. So that's why we say FIFO is okay. That's just first in, first out. That's a normal queue. That's, you know, going to McDonald's or something like that. So here is our solution. So instead of that, we can, if we fail to acquire the lock, we'll add some pseudocode here. We'll just add ourselves to a wait queue for this specific lock. And then we will put ourselves to sleep. Sleep is a bit different than yield, so sleep will just block this thread from executing until another thread calls wake up and wakes it back up again. So it will block until another thread wakes it up. Assume this is you, I don't know, during finals week. You go to sleep, someone needs to wake you up. So, probably a bad example, but anyways. So in the unlock, how we change that is, well, we would change the value from a 1 to a 0, and then we could check. If there is a thread in the wait queue, so say there's 10,000, we just wake up whatever is at the beginning. That's it. So this is a good try, but there's 2 issues from this, because, well, there's probably some data races here. So there are two issues, and we should be able to argue about them. One is lost wake up, so that means, is there a situation where one thread has the lock already and another thread tries to acquire it? Is there a situation where it will just put itself to sleep and then it won't get woken up again? So essentially, it will be in a coma, let's say. So it just goes to sleep, nothing ever wakes it up. Is that a possible situation? And another situation that might happen is creatively named the wrong thread gets the lock, which means, is it possible that there is a thread waiting for a lock and it should be next in line, but is it possible that another thread can acquire that lock before the thread that's patiently waiting gets it? So let's think of this and then see if you can come up with a order of threads executing on a single core. So just by context switching, just by having concurrency, is there a situation where I will have a lost wake up or some other thread will steal a lock from a thread that is currently in the waiting queue? And if we can come up with a situation, that means that our implementation is incorrect, no matter how unlikely those context switches may be. If it is at least feasibly possible, it means that your program has an error in it. Even if you run it 10,000 times and it seems to work, well, you're not guaranteed it will always work. Yep.
I'm not sure if it's the key of the problem here, but in the lock function, say if you keep getting like ones from compare and swap, will that like add the same thread to the queue multiple times, or?
No, so if a thread, so say thread 1 has a lock and thread 2 tries to call lock,
Yeah.
it will check the value will be 1, so it will go into the while loop, and then it adds itself to the queue and then puts itself to sleep.
So basically, it'll never call compare and swap again.
Yeah, so unless something wakes it up. No, unless something wakes it up. So sleep just blocks until someone wakes you up.
Thank you.
Yep.
So would you like, instead of setting L to 0, you'd set it to the first thing in the queue?
Set L to the first thing in the queue?
Yeah. So instead of going unlock, you just hand the key directly to the first thing, to the next thing that's going to be in the lock.
So if I want to hand the lock to the next thread, I would need to change my implementation, but keep that in mind because we'll do that for a better implementation. But given how it's written now, is there a situation where I will get, the lost wake up or the wrong thread kind of butts ahead?
So if one thread is unlocking, it executes L equals to 0, and at that point we have a context switch to have
So here, let us go there. So say we have thread 1 that has the lock, so the lock is currently 1. So you said thread 1 starts executing and changes the lock from a 1 to a 0. Okay? Yeah, you can context switch, so we could. So right now, thread 2 is just calling lock. It's not blocked at all. So in this situation, well, if thread 2 starts executing now, well, it would call compare and swap. The current value is 0, so it would change it from 0 to 1, and then it passes. So it makes it through lock, which is fine. So that seems to work. That's not a problem. So let's reset this.
By the way, sir, is thread 2 in the queue?
Nope. So thread 2 is just calling lock. It's not in the queue yet. Okay, so let's first think about this lost wake up. So is it possible, so if thread 1 has the lock and it's calling unlock, and thread 2 is calling lock, is it possible that thread 2 will put itself to sleep and thread 1 will never call wake up on it? Yep.
If you change it to 0, but the T2 is checking for it at the same time before waking up.
So here we'll just assume concurrency, so nothing happens at the same time. Either thread 2 executes or thread 1 executes. So which one do you want to run first?
It doesn't work.
Doesn't work? Yeah.
So we'd run thread 2 first, compare and swap. It would find that that it's locked, then swap to 1, and then it'll unlock. And then when it adds itself to the queue and then sleeps, or then you swap back to 2, add queue and sleep, and then unlock will have already finished, and so it would be stuck in silver.
Yeah, so to explain that again, let's see. So first, initially, we could have thread 2 executes. If thread 2 executes, well, currently thread 1 has the lock. The value of it is 1. So thread 2 would execute compare and swap. What would it return?
0,
So it always returns the value pointed to it.
1.
So it would turn 1 because it didn't change it from a 0 to a 1 because thread 1 has the lock. So it would go into the while loop. So at this point, we could context switch. So now we could context switch back over to thread 1. Thread 1 can set the value from 1 back to 0. And then if thread 1 continues executing, it will check, is there any threads in the wait queue? Is there currently any threads in the wait queue?
No.
No, so I'm done, my job here is done, so thread 2 just finishes the unlock. Now if I come back to thread 2, well, now it would add itself to the wait queue, so now it's part of the wait queue. Now it puts itself to sleep.
Oh wait, so sorry. So like when thread 2 is like calling on compare and swap, it's still like 1?
Yeah.
It is.
Yeah, so when thread 2 calls compare and swap, because here we said that thread 1 has the lock, the current value of the lock is 1, and thread 1 changed it. So it should not be able to acquire it until thread 1 calls unlock. All right. Yep.
When does thread 2 get into the waiting queue?
When does what?
When does thread 2 get into the waiting queue?
So thread 2 got into the wait queue in this situation right after thread 1 finished unlocking it. So here, we can back up again. So in this situation, if we reset everything again, we're essentially in a situation where thread 2 executed first. Oops. It called compare and swap. It failed because thread 1 has the lock. So it would want to start executing inside the while loop. Now we could context switch before it adds itself to the queue. So we context switch back over to thread 1. It unlocks the lock. It would check the queue. There's nothing in it because thread 2 was about to add itself to the queue, but we context switched away from it because unlucky for him. And then we finished. And then if we come back to thread 2 will just resume. So we'll add itself to the queue, put itself to sleep, and there's no one to wake it up. It's going to miss its final exam and fail the course, which our final exam is 9:30 if you haven't seen that yet, so yay.
It's already out?
Yeah, it's scheduled for December 8th at 9:30.
Ouch. Why is it so soon?
9:30 a.m., yeah. So I will be up at like 4 a.m. that day. Yay. Yep. So you can't make, like the whole body of the while loop? So yeah, I guess I could solve it if I made the whole thing, like I'd have to make that whole function atomic, that whole lock atomic, right?
Just what's inside the while. Just to sleep. Like you not context
So if I just like put a mutex around this, I still have that problem because it could not acquire the mutex until, right? So I still have a slight issue. All right, what about this situation where the wrong thread gets the lock? So let's change our scenario a little bit. So we can start off where thread 1 has the lock, it's calling unlock. So if it starts executing, it would start executing here. Let's assume thread 2 is in the... So if thread 2 is in the wait queue, it should be the next thread that gets the lock as soon as thread 1 unlocks it, right? So let's assume we have a thread 3 calls lock. So is there an ordering by just switching between these threads such that thread 3 will acquire the lock before thread 2 gets it? All right, we all agree with that? That one ended fast. So let's go over that real quick if you didn't hear it. So what we could do is initially thread 1 has the lock. So the value of it is 1. We could start executing thread 1. So thread 1 could change the value of the lock from a 1 to a 0. And then we could get unlucky and then context switch immediately to thread 3. In which case, if we context switch now immediately to thread 3, well, it will do this compare and swap. What's the value of the lock? 0. So it will change. So compare and swap will change the value from a 0 to a 1 to indicate that this thread has the lock. So thread 3 now has the lock. So it has the lock. If for some reason, at this point, thread 1 continued executing, well, it would check the queue. Oh, there's a thread in the queue. Okay, great. I will wake up thread 2, and then I will finish. So when thread 2 wakes up, it would resume right after the sleep. So it would go back to the while loop and then try this compare and swap again. And then, oh no, the value is already 1 because thread 3 came in, swooped my lock. Damn thread 3. So it would see that the value is now 1, then add itself back to the wait queue, sad day, and then put itself back to sleep again. So everyone agree that that is also an issue. Thread 3 butted ahead in line. Thread 2 was patiently waiting there in the wait queue like a good thread. I don't know why I'm personifying a thread, but anyways, it was waiting there. Thread 3 came in, butted ahead. Just rude. So any questions with that? So let us solve these issues. So in the slides, there's an example for lost wake up, which is what we went over. And then also an example for the wrong thread getting the lab, although I swapped the names of thread 1 and thread 2. Doesn't matter as long as you are consistent. So here is our fix, and it looks ugly. Looking at this just looks like a big block of code, but there is a trick to reading this. So let's go here. So the trick to reading this is, well, before in our first attempt at doing this, we essentially had a lock, so the value we were using as our mutex, and we also were maintaining a queue. So the new thing here is this guard. So this guard, we are going to use that as a spin lock. So remember way back here at the beginning, we said that this was a valid implementation of a lock. It just kind of spun. It would try over and over again, but this worked to ensure mutual exclusion. So if we switch back to the big ugly thing, well, This guard we are using as a spin lock, and we will only use that spin lock within this lock and unlock. So this big ugly thing, well, if we wanted to rewrite that as something that's more manageable, this is essentially a lock of guard. And then if we went through, if we set guard to 0, well, that's essentially the same thing as an unlock. To guard. So remember everything between the lock and the unlock. That's the critical section. Only one thread can do that at a time. And we have an if branch here. We want to make sure that whenever we lock the spin lock, we eventually unlock it. That's why we have an unlock in each of the branches of this if statement. Now, if I go back and read this unlock, well, the first thing it does as well is it will try to lock the guard. And then at the end, this line is the same as unlocking the guard. So this is kind of like your idea where I should make the body of that while atomic, essentially, right? So let's see if we fixed this lost wake-up example. So the lost wake-up, what happened was, well, while thread 1 was trying to unlock the mutex, it was done halfway, and then thread 2 woke up, or sorry, we context switched to thread 2. After it knew that it was already locked, and that's how we got into that bad situation. So now in this case, we would have thread 1 and thread 2. One of those goes first, and because the first thing it does is lock the guard, as soon as one of them goes through, you can't context switch to the other thread. I mean, you can, but it's not going to pass the lock. So what would happen? Well, thread 1 could start executing. It could lock the guard, so it could acquire the spin lock. Then it would check if there's anything on the queue. If the queue is empty, all I would do is change the lock. So the lock is our original value. It would just set it to 0. So it would change it from a 1 to a 0, and then just finish. Otherwise, if the queue is not empty, this is your idea here, so that was a good idea, I will just transfer the mutex to the next thread. So all I have to do is just wake up the next thread. If I don't have any data erasers or anything, the value of the lock is still 1, and I just woke it up, so it's going to resume somewhere. It's going to resume after it fell asleep and just finish. It's going to immediately finish the lock. So thread 1 will eventually unlock that guard or unlock that spin lock, and then thread 2 can execute. So in this case, it could acquire the guard. It would check the value of the lock. You'll notice here we don't need compare and swap because, well, if we have a spin lock, we don't have any data races because only one thread can be doing this at a time. So we don't need compare and swap anymore. So we could check the value of the lock. If it's 0, well, we change it to 1 because we now have acquired it. Then we can just unlock the guard, and then we finish the lock call and keep on going. Otherwise, well, we could add ourselves to the wait queue if the current value of the lock is 1. Add ourselves to the wait queue, and then unlock the guard, and then put ourselves to sleep. And then if we put ourselves to sleep, then if thread 1 tried to execute after we put ourselves to sleep and put ourselves on the queue, well, it could get the guard, check the queue, then, well, there's something in the queue, so it would go into this else. Then it should just wake up thread 2, and then it should be able to resume with the lock. So, is there any issues with this, or does this work? Data races are like a fun puzzle you get to solve every time you program now. Yeah.
Okay, sorry. So like essentially, like my understanding of it is just basically like the guard is basically another lock that locks the lock, unlocks the lock.
So a guard is a spin lock to ensure that, essentially to ensure that our lock and unlock functions have mutual exclusion. So only one of them will execute at a given time. Because our problem before was we started executing it, we got like halfway through it, then we swapped to another thread, and that's where our issues came from. So the idea is, yeah, we use a lock so we can implement our lock. So we get rid of data races while we're implementing our lock. Yep.
Sorry, I wasn't really paying good attention, but does this like kind of optimize the CPU usage from like a simple spin lock?
Yeah, so this lock, so it should solve the thundering herd problem. So whenever you unlock, only one thread tries to wake up and acquire it. And it should also solve the problem that we saw before was, it should also solve lost wake up, so that shouldn't happen anymore. And the wrong thread getting the lock also should not happen anymore. So we want to solve all three of those. So,
Yeah, that was what
oh, so is this more efficient than a spin lock? And depends. So if you have a single core machine and you want to be fair and all that, so fairness costs time. So if you want to be fair, you have to do something like this. So fair means you essentially acquire the lock in the same order you tried to, like no other thread butts ahead of you or anything like that. So spin locks don't guarantee that. Spin locks also have the thundering herd problem, but depends on your application. If your critical section is really, really small, a spin lock might be fine. But if your critical section is really big, well, if you have a spin lock, it's going to waste a lot of time just retrying over and over again. So you might not want to use that, in which case this would be way more efficient. Again, situation, if there's like 1,000 threads all sharing this one lock and all trying to lock it at the same time, this is going to be a lot better because, well, it's only going to wake up one thread at a time. The rest are just going to go to sleep, block, they can't execute. Yeah?
Now you're just gonna have a thundering herd at the guard.
So you won't have a thundering herd at the guard. Each thread, so say one thread has the lock and then 10,000 come in to try and acquire it. Those 10,000 threads are all going to put themselves on the queue and then go to sleep.
Yeah, but while one thread is calling lock, but if other thread also tries to call lock, they have to wait.
Yeah, but if another thread tries to call lock while another one is in the middle of it, it has to wait, right? It just happens serially, so we don't have any data races. But
There are a lot of threads trying to call lock at the same time.
yeah, there's a lot of threads trying to call lock at the same time, but the code in here doesn't do that much. Adding yourself to a queue, that's a few memory writes, and that's it. We're just doing a few memory writes, that's it. That's probably a lot better than just having 10,000 threads, each trying to read that value over and over and over again, than just doing like a few memory writes once.
So we are basically still using a spring lock, it's just that we are now having a much smaller critical section for the spring lock.
Yeah, so spin locks are totally appropriate if your critical section is very small. So you might even want to use spin locks sometimes, like the answer is it depends. So sometimes spin locks might be better if your critical section's small. Sometimes mutexes might be better if your critical section's bigger. Also depends on how many threads are trying to acquire it. So there's lots of trade-offs. That's why we have different implementations. All right, so is there a problem with this implementation? A subtle one. And I will give you a hint.
What is happening to guard in unlock?
what is happening to the guard and unlock? What do you mean?
Well, when thread wake up, it cannot set unguard to 0.
So after thread wake up is done, it would just execute the next line and set it to 0 if it continued.
Oh, right. Wake up, that's a context switch.
Yeah, wake up just unblocks that thread, doesn't context switch. I mean, you may context switch, but if you context switch to it, I mean, it just gets the lock, that's it. It would just resume, it doesn't unlock it or anything. Yeah, no. So it's subtle, and the hint is the arrows where the threads are currently at pretty much demonstrate it. Yeah. Yeah, so I could context switch. So let's say thread 1 has the lock, and thread 2 goes ahead and tries to get it. Well, it would get the guard, put itself on the queue, and then unlock, and then it could context switch right now before it puts itself to sleep. And then thread 1 could start executing right before it puts itself to sleep. It would get the guard, and then check the queue. Oh, there's something in the queue. And then it would try and wake up thread 2, which is currently not asleep. So this is a very subtle data race, but it's also not that big of an issue because, well, you didn't have a data race with the queue. So thread 1, if you are thread 1 right now, you actually know thread 2, the next thing it's going to do is put itself to sleep. So if you wanted to fix this, if you just detect that, whoa, I'm trying to wake up a thread that's not asleep yet, all you have to do is just retry it until it eventually puts itself to sleep because you know it's going to. So I only omitted that from the slide just because it makes it way uglier than it currently is. But this actually has a very subtle issue, but you could detect it. So if you try and wake it up and it's not asleep yet, just yield and wait for it to go to sleep. And then you can successfully wake it up. Or if you're implementing this thread library yourself, you could go ahead, you could cancel the next sleep of it or do whatever mechanism you want, but you know what the next thread is going to do. So if you wanted to, in your lab 4, I don't make you write thread sleep and thread wake up, but if you really want to, I took it out, but if you really want to, you can. So feel free to implement that yourself. So last thing, so remember what causes data race. So this is going back to that discussion of, oh, should I use a spin lock? Should I use a mutex? Again, there's a series of trade-offs. So going on with that series of trade-offs, remember the definition of a data race. So 2 concurrent accesses to the same variable, and at least one of them is a write, which implies that we can have as many readers as we want, and we don't have any data race. So you wouldn't even, if you only read, you don't even need a mutex. Only reading is fine. Value doesn't change, nice and safe. So you may be in the situation where you write an application, you want to prevent data races, but writes are fairly infrequent, and you have a lot of threads trying to read. So ideally, you would want, there's 8 threads. You want all of them to read in parallel all at the same time because that's safe. And then as soon as one tries to write, you want to prevent any of the other ones from writing. If they're infrequent, that's pretty good. Otherwise, if you had that scenario, right now all you have in your arsenal is a spin lock or a mutex. In that situation, well, no matter if a thread is reading or writing, only one thread can execute at any given time. Probably really bad for performance. So there is another type of lock called a read-write lock. So this is a special type of lock that has 2, as it kind of implies, it has 2 types of locking calls. There's a lock for writing and then a lock for reading. And the difference between them is if you acquire the lock for writing, you should be the only thread that has that lock, and there should be no other threads trying to read that variable because, again, we don't want any data races. The other side is, well, if a thread has the lock for reading, well, other threads should be able to acquire that lock for reading. They should be able to execute concurrently or in parallel. Likely you only care about parallelism because of performance. So ideally you want them all executing at the same time. So this is how we would implement a read-write lock. So in our implementation for a read-write lock, we could keep track of the number of readers, and we could just have a generic lock to represent our guard. This could be a mutex or a spin lock. In this case, it's the same idea we had when we were implementing mutexes. So we could just use a spin lock because we're only using it internally. And then here is the lock that we're using to represent our mutual exclusion. So it could just be something like a mutex. So the easy implementation for it is, well, in the write lock, we want to guarantee that only one thread has the lock. So we just use that mutex directly. So for a write lock, just lock the mutex. And then for a write unlock, just unlock the mutex. Simple. The harder situation is for the read call. So let's go through it. So it would, let's say it has a spin lock. So it acquires a spin lock called guard. And the idea behind this guard is we want to prevent data races on this number of readers variable because we're going to keep track, essentially we're going to keep track of how many threads are sharing the mutex for reading. So we want to guarantee that there's no data races when we increment this, because we saw when we had that plus plus count example with multiple threads, the value can get inconsistent. We don't want data races. So here we would increment the number of readers. If initially we increment it from 0 to a 1, it means we are the first thread that tried to acquire the lock for reading. So we would just try to lock the mutex directly. If we can lock the mutex directly, we just unlock the guard because we're done modifying the number of readers, and we can just continue. Now, if another thread tries to acquire the lock for reading, it could acquire the guard, set the number of readers from 1 to 2, and then it wouldn't go in this if because they're all sharing that mutex, and then it just unlocks the guard. We could have any number of readers. It could increment from 2 to 4, 4 to 5, 5 to 6, Then eventually, in the unlock, what that will do is acquire the guard, so we don't have any data races with the number of readers, decrement the number of readers because now this thread is not going to have that lock for reading. Then it would check if it has decremented it from 1 to 0, it means it's the last reader, so it should give up the mutex. And then it would give up the mutex and then unlock it. So this way, if we had two threads that have the lock open for reading, well, they are sharing that mutex. If a writer comes along, it's going to sit here at this lock call until eventually there are no more readers anymore, and then the readers unlock that mutex, and then we can have a single writer. So any questions about that? Yep.
Sorry, I didn't actually follow. So it's like the first reader locks the lock, and then like all the following readers will read the data before it locks the lock, and then if a write comes in, then
Yep.
I have to wait for like all the readers to finish and then write the data. Is that all it does? Or?
Yeah, so it's kind of like, I don't know, if I gave you a key to a lecture hall or something like that, it's like the rule, the first person that comes in can use the key, unlock it, and then let as many people in as you want. If you want that lecture room to be secure, the rule is the last person that leaves locks the door when they're done. So it's the same kind of situation. So I'm essentially, I have one mutex, and either one of the readers acquires it and then shares it with all the rest of them until no threads are reading anymore, or a single writer gets it. But because I'm sharing that mutex between this, I'm using the same mutex here, and here for the write lock and the read lock. So I'll either have a bunch of readers or one writer, and that's it, which is safe, right? So I can have as many threads reading as I want, but I should only have one thread writing.
So sorry, so for example, if you're already reading this block and then like the write calls in, then like the write log doesn't actually do anything.
Yeah, so if, say, even one thread has the mutex, like acquired the mutex as part of this read lock, well, if someone tries to call write lock, well, it will try and lock the mutex that the reader already has. So it'll just sit there until it can acquire it eventually.
Oh, so like the write log will be blocked.
Yeah,
Oh.
yeah, so like that lock is just like a normal mutex, so it would just be blocked until eventually the reader reaches this and unlocks that mutex. Yep.
So basically the parity is different to the read, like writes may never execute unless consistently reads and reads. And writes will never execute.
Yeah, so there is a slight problem here because all the readers are essentially sharing that lock. Well, if you have a lot of readers, this unlock might never happen, right? So that is a problem for a realistic read-write lock. So this is just a simple implementation that has an issue. The smart developers that actually implemented the proper read-write lock have thought of that. So ideally, you would want it, if you request the lock for reading, no new readers, or for writing, any new readers that come in should have to wait until you get it for writing. Yeah.
Yeah, so in this case, the log function here is just a mutex log.
Yeah, in this case, there is this lock. It would be a mutex, and it's shared between the readers and the writers.
And guard in this case is actually also a mutex.
Yeah, guard could be a mutex. In this case, it could also be a spin lock. It's kind of small, so like it's only protecting an increment, which is pretty fast. So spin lock would probably be more appropriate, but it could be a mutex if you really wanted it to be.
But in actual implementation, if you want a spin lock, we have to define it explicitly, right? It's the whole.
Yeah, well, so, sorry, in an actual implementation, you can use a spin lock or mutex. They both have a lock. So there's a pthread spin lock, there's a pthread mutex, there's also a pthread read-write lock. So luckily you don't have to implement that, but this is basically the gist of it that gives you the idea. So any questions about that? All right, we are good. So again, summing up all this locking stuff. So we want to prevent data races. How do we prevent data races? Well, we put any code that might be susceptible to a data race in a critical section such that only one thread can execute it at a time. And we should know what a data race is: two concurrent accesses to the same memory location with at least one of them being a write. So our mutex or spin locks are the most straightforward locks. They only ensure one thread is in that critical section at any given time. If we want to implement them ourselves, so we had to implement a spin lock, then we use the spin lock to implement our mutex, and then we could, implement read-write locks on top of mutexes and spin locks. But to implement that spin lock, you need some hardware support, so we need that compare and swap instruction. You would need some, if you're implementing a mutex, you would need some kernel support for like wake up notification for threads. So you need to be able to put a thread to sleep and be able to wake it up. So you would need to implement that. So that's missing from your Lab 4, but if you wanted to, you could implement it. And there's also the case that if we know we are reading a lot through multiple threads and writing infrequently, well, we should probably use something like a read-write lock for performance, because all the threads reading at once, perfectly safe to do. So just remember, pulling for you, we're on this together.